review. I did put a little bit of Unit 6 in there, just because there were some acid-base topics in there. But most of it is Unit 1 for today. So what we're going to do is we're going to go over.
May I steal it for a ruler? Portrait.
Yeah.
Then it's new.
If you need a ruler, there's rulers in the front. I'll pause.
Daniel, can I get a minute? Reminded me. I'm good. Take that as you. So wow. Daniel, can you give me a ruler? You're right here. Okay. Why'd you say Samuel? You said Samuel. Can you give me a ruler? I did? Yes.
So don't lose these cardstocks, or else you're gonna make another one. Unless that's what your strat is, writing them over and over again. Okay, so at the top, you should write Unit 1 revision, acids and bases. And how I did it was I wrote my formulas first, and I wrote them on the very left-hand side. So I wrote formulas, and then I wrote a line down like this. Formulas. Starting with pH, your first formula. pH equals negative log of what? The concentration of H plus. Number 2, the opposite of that. 10 to the negative. pH is what? The concentration of H plus. This is if you have the concentration of H plus, but what if you have a weak acid? What would be the formula for that? We just reviewed it. Ka equals H plus times X minus over HS, which the easy version of that is X squared over HX. Because H plus and X minus for weak acids are always the same. That's weak acid. What if I wanted the pKa and I had the Ka? What formula would I use? I have the Ka, I want the pKa. What would I use? Negative log it. pKa equals negative log of the Ka. What is the relationship between pH and pOH, just in case you wanted to use that pathway? So 14 minus pH is pOH, or pH plus pOH is 14. That usually is the easier math. The alternative way to solve H plus to OH minus calculations is using Kw. What's the formula for Kw? Go ahead.
Concentration of H plus times the concentration of OH is equal to 10 to the negative 14.
You should make a little note about that. Kw is the concentration of H plus times the concentration of OH minus. At room temperature, it's 10 to the negative 14. At room temperature, Kw is 10 to the negative 14. But can they give you a question where they alter the temperature, give you a different pH, and ask you to figure out the K? They absolutely can. And we've seen homework questions like that. So you should write Kw is equal to the H plus times the OH minus, and then at 25 degrees Celsius, Kw is 10 to the negative 14, where the pH scale is derived off of. That's why the pH scale goes to 14. All right, I've got more. There's more.
How about more?
Buffers. So buffers. There are two formulas for buffers. You choose which one you want to write down. You don't have to know both of them. One of them we've already seen, which is the pH equals pKa plus log salt over acid, where salt is the conjugate base that's formed from a weak acid. And what was the alternative buffer formula? There's another.
Concentration.
Equals the concentration of acid over the concentration of salt minus.
So concentration A plus, and then it's the ask formula. Acid over salt times Ka. Like I said, that's the easier one to remember usually, but the math might be a little bit more. There's more. What about KSP? This is a very math heavy unit, if you recall. KSP is always equal to the concentrations of the products, right? So a way to remember it is it's just the products, but it's the concentration of each product multiplied by each other. We'll talk about that in the definition. I put a couple of examples. Uh-oh, I have to put more space for formulas, it looks like. And so I have a couple examples here. If you have Mx solid, and that goes to M plus X minus, what would the KSP formula be for this? X squared. But what if you had M2X? M2X solid goes to 2M plus X minus, what would that be? This would actually be 2x times x, 2x squared times x, and this would end up being 4x cubed. Let's do one more example just to see that we have the idea. What if it was mx cubed, mx to the third? And that was m plus 3x minus. What would that be? KSP would equal, this would be x, but this would be 3x to the third, and what would the math end up being? 3 to the third is 27. So 27x to the fourth. That's to give you some examples on KSP. In KSP, what does x stand for? And mole DM minus 3, right? All right, so that's KSP. There's still one more. KPC. So 10, KPC. KPC is the partition coefficient, and that's the really weird one. That's the solubility of a compound in two different solvents that are immiscible with each other. And so this one is the solubility in solvent A of whatever that is over the solubility in solvent B. And this is when you have, it's this little device right there, two immiscible, yeah, and then it has liquid. But you have two liquids here. This is solvent A, solvent B, and you dissolve a certain amount in each one, and they're in equilibrium with each other, is the idea. The two solvents. So some is dissolved in solvent A, and some is dissolved in solvent B. This right here is called a separatory funnel. Yes.
What does immiscible mean again?
Immiscible means they they're separated from each other.
Okay.
Meaning like oil and water.
Ah.
They have two separate polarities. So two immiscible solvents. And that's all the formulas for acids and bases. That's just formulas. There's more. The next topic is essential reactions. Essential reactions. So first part was formulas. Next part is essential reactions. Reactions. First one is neutralization. What's the neutralization reaction? This is back to basics. What's neutralization? Go ahead.
Acid plus base equals salt plus water.
Acid plus base goes to salt plus water. Neutralization. What's a Bronsted-Lowry acid-base reaction? What would that be? Acid transfers H plus 2A. Or acid donates H plus 2A. Base. I'm going to write an example of that one just so you remember. HCl plus H2O would make what products? H3O plus Cl minus. Where this is the acid, this is the base, this is the conjugate acid, and this is the conjugate base. While we are here, we had a little bit of issue with the next particular topic. If I asked you to find the conjugate acid or if I asked you to find the conjugate base. I recall one exam, I think it was the acid base exam, where maybe 0 or 1 people got the answer correct. 0 or 1. To find conjugate acid, if you're asked for it, what are you supposed to do? To find the conjugate acid. If I gave you just a formula for something, what would you do? You would always add 1 H plus. And what if I asked you to find the conjugate base? Yeah, it's remove. Remove 1 H plus. What does that look like in practice? So if this right here is my base, and let's say that it's a CH3COO minus, what would the conjugate acid of this be? How would we write the conjugate acid? If that's my conjugate base. And if that's my base, what's my conjugate acid? CH3COOH. If my acid is H2PO4 minus, what would my conjugate base of that be? If my acid is H2PO4 minus, what's my conjugate base? When I remove a hydrogen, what else do I need to remove? 1 from the charge, which means the charge goes down by 1. So this would be HPO4 minus 2. And these two are called a conjugate acid base pair. The next, buffer reactions. So 3, buffer reaction. What is required for you to have a buffer? In order to have a buffer, what do you have to have? So you need requires weak acid and conjugate base. Or weak base and conjugate acid. So what if I gave you an NH3, NH4 plus buffer, and I asked you to illustrate how it works as a buffer and to use equations? How would we show that? How would we show how a buffer acts as a buffer?
It was active with the base, with some acid or the base.
To show buffer action, react with strong acid. And strong base separate. So how would that look here? Oh, it's starting at the top. How would that look here? If I wanted to show how NH3, NH4 plus works as a buffer, how would I add the strong acid?
We react with some acid with the base. No.
So you would add H plus for strong acid, right? So which part of the buffer would react, this specific buffer, which part of the buffer would react with H plus? NH3 or NH4 plus? NH3 because it's a base and H plus is an acid. So you would do H plus, I'm going to show it with another color, plus NH3, and that it makes NH4 plus. You do not have to include spectators. You can if you want, but a lot of people get messed up with including spectators. They'll write these compounds wrong. And what would we write for strong base? What would we add for strong base? We add H plus for strong acid, add OH minus for strong base to represent strong base if you don't want to include the spectators. So which part of this buffer would react with strong base? NH3 or NH4 plus? So you could reverse it, the order, and now you write OH minus plus NH3. And what would that make as products? Or NH4 plus. Because that's the acid part. So we put it with the base, and what would that make as products? NH3. The other part of the buffer, what happens to the other hydrogen of NH4 plus? All right. What happens to the other hydrogen of NH4 plus? It goes to the OH minus, making 1. So that's how we do buffer action. I still have a little bit more. What would be the reaction to create a buffer? You actually add to your weak acid, you add to it a strong base, and it makes salt and water. That's the reaction to create a buffer. We saw that in the bell work today, actually, when we did the mole table. We took a amount of weak carboxylic acid, we reacted with strong base, we got salt and water, made a mole table, got the amounts, and then went from there. What about organic acid-base reactions? Are there any organic acid-base reactions that we should know about in this unit? Organic reactions. What are our acidic functional groups? What's the first one you can think of? Phenol? Phenol. Carboxylic acid. So how would they react? So phenol, let's do phenol first. This is an acid. So how would it react with base? What would it become? What would our products be? Ona and what's the other one? Water. So phenol is acidic. What's the other major acidic group? There's one more. carboxylic acid. So if I have CH3COOH and I put that with NaOH, it's going to react and give me CH3 Kuna and water. And what functional group is basic? These are acids. There's one functional group that's basic. It's called N. That's only slightly basic. It actually doesn't do acid-base reactions normally. It's amine. Amine of like the amino acid. Amine is the only basic group. Amine. So if I had CH3, NH2, how would that react with acid? The same way that any other base would, which means you get CH3, NH3 plus. Amides don't do this because amides are neutral. And guess what? That's the first half of the page. That's this half. Now I have this half to do. So we've done the formulas and we've done essential reactions. But what are the other things you need to know for your one-pager? Definitions and explanations. So on the other side, you're going to flip your paper so that you have definitions and explanations on the other side. So on this front side is formulas and reactions. And then on the back is definitions and explanations. Are you going to fit everything in one page?
Which one's the acids for your organic reactions?
What? The acids are phenol and carboxylic acid. They do any regular acid-base reaction. They just do the regular acid-base things. That's just something to remember. All right, let me know if we're good to move on.
No.
No, not yet? I will toss.
How did I gonna use that too? My.
How did I use the whole page? I just kept writing so much. So what I used is attach this paper here, all the syllabus definitions, I attached them. And so this is all the syllabus that we're going over today, pretty much, which is a part of the syllabus, not all of it. A small part of the syllabus, actually. It's just acids have so many formulas. Ready?
No.
No? Okay.
And ready for my right.
Oh my God. Are you sure?
So what do we have? Definitions and what else?
The other side is definitions and explanations.
Yeah.
Like I said, I did it all. I did it. To save you time, I found them all the official definitions.
Thank you.
Found them all.
Or you caught them all. Like look at.
Caught them all. Ready? Nope. No, still no? Okay. Let me know. Put your thumb up when you're ready.
You know, my brain is fast, so
Which acid
We do have time, but we still have this whole page to go over.
I want this room to be absolutely.
Damn. Don't we all?
Super the time to remind you that I am recording right now.
Oh my God.
I did say that.
I'm ready for
You don't regret
Wait, so I can put 6, 7 in the break ready.
6, 7, 6, 7,
Trying to call yet?
6. Yes.
Okay, good.
So that anybody who's missing, like Thursday, aren't some of you going to be missing? There's something called honor roll.
Oh yeah, we are. Good Sunday.
Unless you decide to do this review with me instead of go to honor roll.
Are you checking this?
And make 6. So don't lose it. I am checking it. It's a great. Ready?
No, could you
Uh-huh. Yes, I'm checking it. It's a great. To not lose it. Otherwise, you have to write it again. But don't leave it. Okay, we're ready? Anybody else? Good for the next slide? All right, I'm gonna go ahead and keep this precious content. All right, flip to the other side unless you are attempting to get everything in one page. Good luck. On the back, I put on the left-hand side syllabus definition. These are the defined standards, or explain what you mean by. That means word for word keyword definitions. And in A level, there are a lot more of these than in AS chemistry, if you'll recall. So here we go. The first one is actually conjugate acid-base pair. That is the first definition that they say you need to know. Conjugate acid-base pair are two substances that differ by one H plus. Conjugate acid-base pair. That's the first one. I'm going in syllabus order. The next one in syllabus order, they want you to know word for word is a buffer solution. What is a buffer solution? So what is a buffer solution?
A solution that resists pH change when small quantities of strong acid are present.
Yes. A solution that resists changes in pH, and that gives you 1 point typically. The second point is to say when small amounts of acid or alkali are added. And if you wanted to say less, you can say H plus or OH minus are added. Solubility product is the next definition, and this one kind of the word I have for it is clunky. It's a clunky definition. It's not the most fun. It's the product of the concentrations. This is the one where you say it's the product of, because it's the multiplication of the concentrations. So it's the product of the concentrations of each ion in a sparingly soluble salt, in a saturated solution of a sparingly soluble salt at 298 Kelvin, raised to the power of the concentrations. Raised to the power of the relative concentrations is the word for word definition. Last night I was on Notebook LM and I was testing the resources, and you can have it make you flashcards on, like, for all of these, and you can have it make a quiz. I was checking the quiz. It basically took and made practice questions similar to the ones in the lessons. So Notebook LM is a resource that I think might be helpful for you as you're studying each of these units.
Has been my go-to speedrun method before every exam. Has worked like 30% of the time, but that's just because I'm bad at chemistry methods.
The next definition, common ion.
I once got to say something about 5-bond particles. Actually.
Common ion.
I once made it use it.
Effect.
It worked.
What is the common ion effect? It's a very common question. The reduction of solubility of a dissolved salt by adding a compound that has an ion in common. last straight up definition in these standards that I included. And this was another clunky one. I think all the K's are clunky definitions. Partition coefficient. So what's a partition coefficient? The ratio of the concentrations of the solutes dissolved in two immiscible solvents in equilibrium with each other. Those are straight up definitions.
Are the explanations longer?
Definitions, explanations. Because I put all of our organic acid base ones in there too. Because then we have a lot of explanation questions with organic acids and bases, like which one's more acidic, which one's more basic. I figured cover all our bases now. Aha, bases. Aha.
I knew you were gonna say that.
Common explanation.
What's it say? Invisible?
Common explanations. We'll start with some easy ones. Pause a little while because you're still finishing the definitions. Get like a minute and then we'll do this. What is a strong acid?
Are you looking for an example or what makes an acid strong?
H plus.
Oh, phenol,
Dissociates completely in water.
Dissociates H plus completely in water.
phenolate.
So I said easy. We're gonna start easy. Dissociates H plus completely in water. So then strong base. By definition, dissociates OH minus. So what's the key difference between strong and weak? What is the key wording difference? Everything is the same except partially. Instead of completely, you use partially. So weak acid would be, I'm just going to point an arrow and put partially. Weak acid, weak base. Instead of completely dissociate, we're talking about partially dissociates. That's the key difference. That's the first one. And these, I'm starting with like the AS chemistry, pre-AS chemistry ones. Because can an AS or even a pre-AS chemistry question show up on an A-level exam? Absolutely. They could literally ask you, what is a weak acid? And you have to know. What about just what is a Bronsted-Lowry acid by definition? Yep. That's all you gotta say. Donates H plus. That's like 8 letters. And a charge.
A lot of reach.
Bronsted-Lowry base. It doesn't donate it. Receives, right? Or accepts H plus. These H plus. Takes H. Are you trying to like do less letters?
Give H plus, take H plus.
Least amount of letters necessary. Okay, so those are the simple definitions. now we're gonna go into the a little bit more complex definitions. Yeah, thank you. Yes. Thank you. Explain the acidity of phenol. Now we're getting to the organic explanations, all the ones that you have to know. Explain. The relative acidities. Or explain we'll start with acidity of phenol. This is a literal standard. Acidity of phenol. Before we get to those explanations, I'm gonna write some side notes up here. What does the EDG do? This is an electron donating group, and what does it do for acidity?
More basic.
It makes more basic. Yes.
Oh, yeah. Oh. I was thinking of anything.
Weakens acidity. Strengthens base. Why? But como?
Yeah, electron donating groups, we found the bond between H plus and the electron donating group, meaning, wait.
An electron donating group strengthens the bond, the hydrogen bond between, and it's not the hydrogen bond like you think the intermolecular force, but just the bond between hydrogen and, for example, a nitrogen or an oxygen. So an electron donating group, because let's say that it's like the CH3, and I'm going to use this OH, alcohol. Because this is an EDD, it's an electron donating group. Methyl groups are electron donating groups. They donate part of their electron cloud into the OH bond, strengthens the bond, which means higher bond energy. If it's a stronger bond, it has a higher bond energy, which means it makes more energy to break it takes more energy to break the bond, which means the H plus is less likely to leave. So strengthens bond, higher bond energy. H plus does not break off easily. Which means that it's not a stronger acid, it's a weaker acid. It's a stronger base. So remember, weaker acids are stronger bases for the same reasons. And so what about an EWG? What does that do? EWG, which is an electron withdrawing group. Electron withdrawing groups have high electronegativity. They pull the electron cloud away, and so they will always make a stronger acid and a weaker base. I have more to say here. What about phenol specifically? What happens with phenol? And phenylamine, technically, if they want to ask you, they could ask you about phenylamine because they technically have the same thing going on with both of them. With these, a lone pair of electrons from both the oxygen and the nitrogen, if it was phenylamine, actually donate into the ring. So electrons donate into the ring. So the benzene acts, the localized electrons act as the electron withdrawing group, pulling the electrons away. Electrons donate into the ring.
The colon looks like a pair of electrons next to the benzene.
Oh, this? I'll just erase it. Bye. And this becomes part of the localized high bonding system. So anytime you have phenol or phenylamine, you have to talk about the pair of electrons are actually going in to the ring and becomes part of the delocalized system. And so because the electrons are going that way, it weakens the bond between the O and the H, which means that the H plus is more likely to break off. So now explain the acidity of phenol. Phenol is acidic. Why? Due to lone pair of electrons on oxygen, which delocalize into the pi bonding system. And what is the other part? There's another mark here.
Yes.
Yes.
It says due to which nuclear.
Due to electron. Delocalizing into the pi bonding system in the ring. There's another mark. What's the other mark? Weakening of the OH bond. Weakens OH bond. H plus breaks off here. For the other ones, for safe space, for the explanations, you're either going to use the concept of electron donating group or electron withdrawing group. So what are the other orders you have to know? You have to know, and I found them from the standard, so I'm writing them down. So relative acidity one of the comparisons they want you to make is water, phenol, and ethanol. Water, phenol, ethanol. What's the order? From most to least. What would it be? What's the most acidic to what's the least acidic? Water, phenol, ethanol. Yep. What's the most? It's phenol, water, ethanol. What about carboxylic acid, phenol, ethanol? That's another comparison that they ask for. Relative acidity of carboxylic acid. And they said carboxylic acid, phenol, ethanol. Do we have the order for those three? Most to least again. Carboxylic acid, phenol, ethanol. What's the most acidic of those three? Which one's more acidic, carboxylic acid or phenol? What do you think? It is carboxylic acid. It's got the double oxygens is more electron, like the C double bond O is more electron withdrawing than the benzene ring. So it's carboxylic acid is more than phenol, which is more than ethanol. You all got more space because I have two more things. I'll pause. Maybe that's what it is. What about chlorine substituted carboxylic acids? Relative acidity of chlorine substituted carboxylic acids. What's the trend? That means how does the amount of chlorines affect the acidity?
Like more chlorine make more acid.
Yes, more chlorine, more acidic. That is literally the trend. Tried. There's more. But I'm going to pause here. Let me know, give me a thumbs up when you're good, because I actually have to change the slide again to add a couple more things. that are also in the standard.
Oh,
Just a couple, like two more.
What did it CL sub carboxylic acid?
Relative acidity of Cl substituted carboxylic acids. Meaning you have a carboxylic acid and next door to it, you have a carbon that has a chlorine or two chlorines or three chlorines. How does that affect the acidity? The chlorines are electronegative, which means they're electron withdrawing. So the more chlorines you have, the more acidic your compound is going to be. And so this is how you can increase acidity. So see some people already, so I'm gonna pause. And then I have just a couple more things to add. Don't lose this paper, or you have to rewrite it all over again.
Daniel, how does your paper look? How does your paper look?
Not too bad. More or less working.
That is really bad. Oh my goodness.
Yep. You shouldn't put it on.
We have to. We have to finish.
Good now?
No.
No? Pause it. Still have a couple more things to add in. There's a lot of acid physics in this class, right? And I didn't even include Zwether ions. I put that into unit 5 because that's where it is. I didn't even. I was like, I don't have space for Zwether ions right now.
Right, those things.
Yeah,
Oh.
amino acids. We gotta talk about those.
How many times do
I still see some writing, so I'm pausing. I have 2 more things I need to cover though to be done.
Yeah, I told you I could fit it all. We've done one.
You got space for 2 more things?
Yeah.
I think depending on how hard, I think I might have space. Maybe.
While I'm waiting, I think I'll just assign that homework.
communists?
What?
Also,
Are you saying what to the homework? Unit 1, homework, acids and bases. I'm making the deadline for the homework Sunday night. But you can do it anytime before then.
All right, good now? If you need me to, I can go back, but I do have 2 more things to cover. Okay, so the next, how do we address the basicity of amines? Why are amines basic? Why? Why are amines basic? So like, why is it basic? Why is it basic?
CH is donating.
So the electron donating groups strengthen the bond between the N and the H. So EBG strengthens, and no EBG you cannot write on the camera exam unless you make a key on the side that says EBG is electron donating group. Like if you make a key on the side for them to read, then they'll
Like for every question or?
think so. Yeah, everyone where it would show up, you don't need to say EBG is this
which would cost you more time than just writing.
electron donating group.
Or you could just put like electron donating group and
For
then
the
like.
first time ever on the 2025 paper, I saw them refer meta director. They put it as an option. So I wonder if they're like
Because
switching
meta
over.
is correct. So you,
Yeah,
you
it's
can't.
ortho para for 2-4, and it's 3-5 is meta. But I've never seen them actually reference it on a mark scheme, and they did. And I was like, maybe they are going to move to like in one of the syllabi, like change to accept it as like a regular answer. All right, EDG strengthens the bond between N and H. Lone pair of electrons on nitrogen can accept H plus easier. That's the idea. So what would happen if I had a secondary amine or a tertiary amine? Would that strengthen or weaken basicity? It would make it more basic. So more EDG equal more basic is the idea there. More electron donating groups around wherever the base is in question will make it more basic. Why are amides neutral?
Because it's an acid in this way.
Oh yeah, an acid and a base react to make that carboxylic acid and amine. But why is the structure of an amide neutral according to structural characteristics here? The NH2 would be basic because it's got that unshared pair of electrons, but it's right next to an electron with drawing curve. So the idea here is that amides are neutral due to NH2 being basic, but C double bond O being electron withdrawn. Basically cancels out the effect of NH2 being a base. And so because Luke is absolutely correct, because an acid and a base react to make an amide, and amide ends up being neutral because that's both characteristics. It has the characteristics of both an acid and a base, so it's neutral. And because it's neutral, you cannot do acid-base reactions with amides, which was an important thing in hydrolysis that you needed to remember. You can't do standard acid-base reactions like this won't accept an H+, and it won't give an H+ away. It won't act as an acid or a base. So it does not act as an acid or base. Does not act as acid or base. Won't give H+, won't receive H+, won't do there. Leave the amides alone. First, you have to know you have an amide, and then you have to know to leave it alone in an acid-base reaction. That's one way they try to trick you in questions. They'll give you an amine in one part of the molecule and an amide in another part, and you have to know to react with one part but not the other of the molecule. So that's important that I wanted to bring up. The very last thing. Going back to Ka. The bigger the Ka, this is a trend, an essential trend. The lower the pKa. What does that tell us about the strength of the acid numerically? The bigger the value of Ka, the lower the number of pKa. What does that tell us about the acid? It's stronger. Because oftentimes you'll be asked to compare either Kas or pKas and just say which is the stronger acid. And so you have to know the larger pKa means more products, right? So more dissociation. Larger Ka equals greater dissociation of H+. Is the concept. That's why. And that's it. That is your first one pager.
So I'm going to go ahead and stop recording at this time.